I'm Tom Ptacek, and we are here today to talk about detecting virtualized rootkits.
So I'll cover this real quick. We're going to cover how Blue Pill works and how basic VT rootkits work. Vitriol, we're going to explain why nothing is 100% undetectable. There's always something you can observe in a system. We'll talk about our implementation of a test framework and the particular tests we used that allowed us to issue the rootkit challenge. And then finally, we're going to talk about where this is all going to end up in, say, 10 years, where basically you're stuck in a cat and mouse game, and it's exactly like the AV ecosystem we have today.
Let's try again. Any better at all? I assume so. You can raise your hand again if I'm totally inaudible. So, like we said, to start with, we want to talk about how hardware virtualized malware works. In particular, how our hypervisor rootkit, Vitriol, from last year functions, and then what we understand to be the differences between our hypervisor rootkit and Joanna's hypervisor rootkit. So, to start with, we want to put this in context. So, there's been an arms race of stealth malware, of rootkits and of viruses trying to hide themselves from detection code for as long as we can remember. You go back to the early 80s, and there's that famous apocryphal story about the compiler backdoor, which when it compiled the login program would inject a backdoor into the login program. And when the compiler compiled itself, it would insert the compiler backdoor into the compiler, which, by the way, is far more clever of an attack than almost anything, maybe save Joanna's work. Far more clever than most of what we see from malware authors today. But this arms race proceeds through, for instance, Dark Avenger and the MTE polymorphic viruses stuff. So we had polymorphic viruses, and after that point, so we entered the epoch of much harder to detect viruses. In the 90s, we had kind of a race through the rings of the operating system, starting with HideSource, the original Solaris rootkit, which simply backdoored the login program, a userland binary, and kind of proceeded through KVM, the interface that userland uses to speak to the kernel. And from there into the kernel itself with things like Josh Damont's amodload, which actually built an entire new module loading interface into the closed source Sonos kernel. So we've seen this notion of kernel malware and kernel rootkits, things that insert backdoors into computers but use the operating system or the capabilities of the environment to hide themselves, going way, way back. And that goes through the late 1990s with the IAT rootkits and the SSDT rootkits and backorifice and
One of the key things here is that we've seen this before. We've seen someone claim the sky is falling. There will be some kind of rootkit that won't ever be able to detect. It'll be in the kernel. You won't be able to do anything about it. And people have always found countermeasures, and we expect this is going to continue the same way.
So getting into the actual technical detail right now, one of the things that I want to make clear to you is that the way hypervisor rootkits work, or hyperjackers work, differs from what you're probably thinking of if you're familiar with virtualization, but not familiar with hyperjacking and virtualized malware. So we have this concept of like what VMware does, where you have a guest operating system running completely contained by the virtualization environment. So it's not doing anything that isn't in some way, shape, or form controlled by the hypervisor. So you have the operating system effectively running on top of the hypervisor. And I think that last year when we introduced the notion of hypervisor rootkits, people kind of walked in with a misconception about how these things work, namely that what a hypervisor rootkit is a very slim hypervisor that you would install under the operating system, and that can install itself and uninstall itself on the fly. That's not really true. What we're working with is a concept that's slightly different from virtualization, and we call it hyperjacking. And hyperjacking is the idea of using the virtualization capabilities of your platform, in our case, the Intel VT instructions that allow Intel hardware to be virtualized, to set up a trap handler so you can intercept certain things that the operating system is doing with the hardware. This is different from what real virtualization is doing because you haven't taken over all of the hardware interfaces that the operating system is using to speak to the hardware itself. If you had to do that, you'd have a problem that was as hard as what VMware has to do. VMware is a multi-billion-dollar company with very smart engineers gradually replicating all the device driver stack used by the operating systems that they emulate. Hyperjackers don't do this. They're much smaller than that. Most of the operations that a hypervisor rootkit is dealing with are passing directly from the operating system to the underlying hardware.
So please elide this from your memory, the slide in the middle, because no one actually implements it this way because it would be an untenable solution.
So again, the native operating system is speaking directly to the hardware. Think of the hypervisor rootkit as in some way running alongside the native operating system and simultaneously punching the running operating system in the nuts. That's essentially what hyperjacking does. Now, if any of you guys are familiar with web application penetration testing, and this is a labored analogy, but I'm going to try it anyways. If you've ever tested a web app, right? Well, you know that you don't have tools that are customized to every single web application you use. What you have is a web proxy in the middle, right? So most of the complexity in a web application lies in the endpoints when you're testing it. It lies in the browser, and it lies in the web server. And if you want to test that and find vulnerabilities and exploit vulnerabilities in web applications, what you do is you put a component between the browser and the web server that passes almost all of the operations for that web application directly between the browser and the web server. And what the proxy does is it allows you to pick and choose which operations to look at and which operations to modify. And in a web application, modifying means inserting a single quote in a field or something like that, right? Well, it's very much the same thing with the hyperjacker. Like I said before, the hyperjacker isn't getting in between the running operating system and all the different pieces of hardware running there. What it's doing is it's picking and choosing which hardware operations to intercept and to work with. But like in the web browser scenario, most of the complexity in this environment resides in the endpoints. And we're going to use that phenomenon here against virtualized malware. One thing I want you to keep in mind is because the hyperjacker itself, because the virtualized malware like Vitriol, because that system doesn't implement all this logic, but instead passes it through, it's quite small and quite easy to implement. It's much less complex than you might think it is. So one of the things that made this so easy to actually infect other computers with was how small it was and how easy it was to load. Vitriol is less than 2,000 lines of code. It does very little. It's just that what it does is, pretty dangerous.
So I want to talk a bit about the level below the instructions. When you think about machine code and malware and stuff like that, most of the things you're thinking about are instruction level state. For instance, if you hook the SSDT, that's changing some instructions in memory and some tables and stuff like that. And this instruction set has a whole other computer implemented below it. Most people aren't aware of this because you don't work at this level, but if you're Intel or AMD or people like that, you're intimately concerned with this. Basically, every instruction you have is implemented as microcode. There's actually micro-ops and small instructions that are within the CPU. They're software updatable. Some BIOS updates contained signed microcode updates as well. And these microarchitectural details are then affected by the side effects and the various components that are used to implement these micro operations. For instance, things like the cache, instruction scheduling, branch prediction. All of these items are microarchitectural details that are influenced by the actual micro ops that are running within your CPU while it's executing instructions. And if you go below that layer, you even have a whole set of embedded hardware or external hardware peripherals that each have their own CPUs. A friend and I once tried to count how many CPUs you'd find in a typical desktop or laptop system. You got about 20 to 40, depending on the type of system, CPUs in there. You've got a CPU to run your display. You've got microcontrollers for your keyboard, mouse, power management. You've got basically your wireless chipset. Most of them commonly have like a MIPS or an ARM firmware on board. You have all these different complex computers within your computer, and you basically have like a chipset LAN within each computer. And you can use that against the hypervisor because the hypervisor isn't aware of the state of the peripherals unless it was intimately familiar with every peripheral and emulating it or potentially custom designed to trap a particular driver's access to that hardware. So what you end up with is an increasingly complex set of state, which is contained within the chipset in the computer, which isn't visible at the instruction level, but you can observe side effects of that. And here in this loop of arrows, we show a typical VT operation, where you're running a hypervisor and some instructions run, and you do something like RDTSC or CPU ID, which causes a VM exit. So that traps to sort of the VT component, VT microcode of your processor, which then decides whether or not, based on what trap flags are set, to jump to your VM handler. So we showed in this case it decided to virtualize it. You're trapping this particular operation. And that jumps back to instruction level execution. And it has some effects at the microarchitectural level. For instance, if you're virtualizing a read MSR, for instance, the read MSR instruction is actually not executed. Instead, the trap happens before the RD MSR is actually executed. And so it begins executing other instructions. And this is a nice low-level interface to the hardware, but it doesn't tell the hypervisor anything about what's going on below that level, at the chipset level, at bus level, hardware level, and other microarchitectural side effects that may occur because of this jump through the VM exit handler.
So let's talk really quickly about, with that detail in mind, and hopefully that helps you understand Vitriol a little bit better, how Vitriol actually works and what that actually looks like in the real world. What Vitriol does when it loads itself, Vitriol, our Intel VT rootkit, or Dino's Intel VT rootkit. What Vitriol does is it installs from a kernel module. So unlike Joanna, which we'll get to in a second, we didn't come up with a clever way to load it under Vista. From kernel mode, what it does is essentially it forks the processor, or it forks the machine into a guest machine and a host machine. And when we say fork, think of it like Unix fork. What you're essentially doing is you're taking the running context of the computer, the registers and the memory areas and things like that, and you're loading a separate guest operating system that shares exactly the same memory segments, the exact same state. So once loaded, the hypervisor and the guest operating system, and when we say guest, we now mean the hyperjacked version of OS X running. Once it's running, the hypervisor and OS X share the exact same memory. They're just code. They're regions of instructions that get called under different circumstances. Think of the hypervisor as a different kind of interrupt handler running on that computer, and then it's using VT to hide attempts to actually detect it. So one of the things that does is it allows Vitriol access to everything in the running operating system, which allows operating system level backdoors to run much simpler, because it's essentially it's the same machine, the same memory, just running in two slightly different contexts. We introduced this idea of, you have user land in a conventional operating system, which runs at a lower ring of privilege. So your user land is ring 3, right? And under that, you have the kernel, which runs in ring 0 with direct access to the hardware. And what virtualization, Intel virtualization and AMD virtualization does is it kind of sort of introduces a notion of a ring -1, which is where the hypervisor itself lives. And what happens is once it's installed and once the trap handlers are set up and once it's configured to intercept certain operations, certain instructions, like we said, instead of talking directly to the hardware, talk to our trap handler instead. And what you get is when you issue one of these instructions, like trying to read a model-specific register from the chipset, right? What happens is you get what's called a VM exit, which is the guest operating system, OS X, exiting from ring 0 and dropping down to the hypervisor to actually implement that instruction. And for the most part, what happens when you do that is the hypervisor itself issues the real instruction. Right? So if you're trying to read an MSR from the chipset, for instance, the hypervisor itself would proxy that request directly through. It's going to allow most of those requests to go through unscathed. It's going to get the result. It's going to populate the state of the computer to emulate the effect of that instruction. And it's going to return control back to the guest operating system. That transaction is called a VM exit, which is exiting from the guest operating system, and a VM entrance, which is returning control back to the guest operating system. Now, like we said before, the hyperjacker gets to pick and choose which ones of these operations are actually going to be virtualized. So certain things, certain ways of talking to the hardware are not intercepted by the hyperjacker. For instance, certain interrupts and things like that will pass directly to the hardware, will not get trapped by a hyperjacker because it's not emulating everything. But certain other things will cause VM exits, and some of those things have to happen. Some of those VM exits and VM entrances are mandatory. So we've been talking so far about how Vitriol works and generally what Vitriol is. And I just want to contrast this with Joanna's Blue Pill. Some of you guys may be familiar with the challenge that we issued to Joanna. We didn't expect to get as much PR from that as we actually did. But Dino Daizovi and Joanna Rukowska released hypervisor malware, released hardware virtualized malware last year at Black Hat simultaneously. And their implementations, the underlying implementations are somewhat similar, but Joanna's is different in a couple of different ways, right? Joanna's hypervisor rootkit uses the AMD virtualization set, which is compatible enough with Intel's virtualization that Zen treats them almost like the same thing. Hers infects Vista and not OS X. Ours is an OS X rootkit. Hers is a Vista one. She has a clever way of loading her rootkit. We didn't come up with a way to compromise the OS X kernel. There are probably already plenty of other good ways to compromise the OS X kernel. We didn't come up with a new one. Hers implements network I/O. Dino's slide deck from last year has, as soon as we figure out how to do network I/O with Vitriol, we'll tell you how that works. Then we went to the conference and saw Joanna present hers, and it's like, why didn't we think of that? But Joanna uses the debug registers in the machine to intercept the network stack calls, to intercept frames coming to the machine. And using that, she's loaded an entire IP stack into her hypervisor, which is just damn cool, right? We haven't weaponized our rootkit to the extent that she's weaponized her rootkit. Ours is more of a proof of concept than hers is. And then she's done more things than we have with our rootkit to prevent people from detecting her. So for instance, you can virtualize the running machine, and ostensibly when you do that, you should be exposing all the operations of the underlying machine, including virtualization itself. That's nested virtual machines. So in a virtualized version of Vista, you should be able to run other virtualized guest operating systems under that. You can't do that with ours. If you issue VM instructions in ours, we trap out. Joanna is actually apparently implements, as she said, she implements nested virtual machines. We don't know the extent to which she does or doesn't do that. What we're doing is we're giving her the benefit of the doubt. What we want to talk about are ways to detect hardware virtualized rootkits, even assuming that she's implemented everything that we can come up with that you could possibly implement to evade these types of attacks. But let's make it clear that she's done more than we have to make her rootkit harder to detect. And then her central claim from her talk was, this is the foundation. Blue Pill itself is not 100% undetectable, but it's the foundation of a path that takes us to 100% undetectable malware. And we're really interested in debunking that claim. We're not sure that anything is 100% undetectable, and we think it's a really interesting challenge to go back and forth between us and her to see whether or not this is true. And I think it's hard to prove whether or not your stuff is 100% undetectable if you don't have an adversary trying to detect you, and that's what we're trying to provide here.
So here's the central claim of our talk, which is that nothing is 100% undetectable. Every potential rootkit that's been out there we've found ways to detect it. So Peter is going to talk a little bit about detecting software virtualization.
So when people talked about virtualization previously, most people thought about the software-based virtualization, and no one seriously thinks those are undetectable anymore. We have, for example, in Virtual PC and VMware, emulated hardware, which is, in the case of VMware, the chipset is from the Bill Clinton president era, and it's really, really old now. We have the holes in virtualization itself that, as demonstrated by Red Pill, the SIDT instruction reveals that the system is virtualized. In the case of Virtual PC, we have a motherboard whose manufacturer is Microsoft, despite them claiming they're not in the hardware business.
Can you fix the mic? We can't hear very well.
Just wait a second.
In the case of registry keys, that at least when the tools are installed in VMware, they will import registry keys from the host into the guest session. And while these are easy to remove, the strings that appear in the video and system BIOS are not quite so easy to remove, and there are many, many of those. There's also the guest-to-host communication channels. There's an explicit API for both VMware and Virtual PC. In the case of VMware, a simple I/O port is accessed using particular registers. You can transfer memory and data back and forth. In the case of Virtual PC, they use illegal instructions and illegal encodings of certain instructions, but in the same way that you can transfer memory to and from the host of the guest and vice versa. The timing variances are visible after a while as well, because you can query the read TSC, which is very, very difficult to trap for a software-based virtualization. And because the host can be queried for the real time using this API, you can see that the numbers diverge after the host has been running for a little while. So clearly, the software-based virtualization is very easy to detect, and we think the same thing for the hardware-based virtualization.
And we thought it was kind of important to point out the fact that software virtualization is straightforward to detect, because like all of you, we take our cues on how to secure things and what is possible and what is not possible from Slashdot comments. And our story got Slashdotted, and before this talk, we actually read through all the different +5 comments that were on Slashdot about whether it would be possible for us to detect Blue Pill. And a lot of them came down to things like, well, they're running VMware, and VMware is undetectable because it controls everything. And if you take away one thing from this slide, it's that if you're using something like a heavyweight virtual machine monitor, like a heavyweight hypervisor, like VMware provides, it's providing a complete containment environment that makes no attempt whatsoever to hide the fact that you're virtualized. If you are running malware containment environments that are trying to run things in simulation, it's more likely that you're going to see malware that takes advantage of virtualization by hiding itself when it detects that it's virtualized than it is that you are likely to see malware that's going to implement hardware virtualization. Do not assume that your malware cannot detect the fact that you're virtualized. Software virtualization is trivial to detect. Kind of the research project that we're working on right now started when we read Peter Ferrie's paper, which introduced one of the detection mechanisms that we're going to talk about later for hardware, but also just a huge variety of different ways to detect different hypervisors, such as parallels, which you can detect and crash with a single instruction, or VMware. So software virtualization is trivial to detect.
So we wanted to give you guys a mental model of how you think about different rootkits and the layers that they're implemented at. For instance, here's a typical kernel malware where, for instance, maybe it just infects one system call or just the SSDT in Windows. And it's a very small hook into the operating system. And it does its best to hide from other aspects of the operating system. And it has a wide variety of places where it can insert little bits here and there to try to hide itself. And it's difficult to detect kernel malware often because there's so many possibilities there. With x86 hardware, it tends to have a huge cross-section because there's so many different variants of it. There's so many different components to it, and it presents a really large cross-section. So keep this metric of cross-section in your mind as we're talking about this. We call it basically the amount of the original system that a rootkit must emulate to remain hidden. So the rootkit has two choices. It can either leave things unemulated and just pass them through, or it can try to emulate the entire behavior of that and trap all the behavior and try to avoid having any detectable difference between it and the actual hardware. Well, both of these result in a situation that's bad for the rootkit, because in the first case, if it tries to trap and if it fails to trap and emulate a feature, then we just use that feature to detect the rootkit. On the other hand, if it tries to trap and emulate a complex feature, let's say the cache behavior of 15 different models of Intel or AMD CPU, you end up with this ton of code there, and that code has a huge code base. It has a huge footprint, has huge cross-section. And the side effects of that code and potential bugs in that code and things like that make it very easily detectable. So in either situation, if you take it to extreme, you end up in a situation where the rootkit author is at a disadvantage. And remember, the entire x86 hardware platform, it's a huge cross-section. There are so many different CPUs, as we talked about before, microarchitectural details, and all of these are observable from a targeted detection algorithm.
So, I mean, if there's one point that we want to make in the whole talk for you guys to take away is you can measure almost any piece of malware by its cross-section. JavaScript malware has a cross-section. Kernel malware has a cross-section. Firmware malware that lives inside of the op-ROMs in your different peripherals has a cross-section. And if you want to evaluate malware by the size of its cross-section, by the likelihood that it's going to miss something or screw something up that you can detect, the entire x86 platform is a poor choice to actually attempt to insert yourself. It's much better to insert yourself in the kernel. You have a million different places that you can hide there. There are kind of nuclear options that you have to detect kernel malware, but they're not the most common options. Whereas if you're virtualizing yourself, you have one single fixed stationary target. Are you virtualized when you did not expect to be virtualized? And that's the cross-section that we want to exploit here.
Good example is the CPU ID instruction. It actually has a mandatory exit, meaning that you have to trap it, or it causes a trap whenever you have a hypervisor loaded. And in its normal behavior, CPU ID has a very specific small footprint. It only takes a few cycles. It doesn't touch memory, doesn't touch the cache, doesn't touch anything else. It just basically stores a few values in the registers. And if you're virtualized, it has a huge impact because there are microarchitectural things that happen because you're jumping and running an entire VM exit handler. You're transferring control to things at the instruction level, which then have microarchitectural impact later on. And this is what makes it easy to detect.
You know, what I think is when it's actually, when we do questions towards the end, we can get you a mic and I can hear the question better. Also, we're introducing this concept of side channel attacks and things like that, which will introduce themselves many, many, many questions. Please evaluate our talk by whether we answer those questions before you have to ask the question. So I'm sorry if it's taking us a while to kind of get to the point on this, but we're getting to it right now, actually, which is we think that all the strategies that we're going to use or that people are going to use to inevitably detect hardware virtualized malware are going to fall into one of three strategies. The first strategy is side channel attacks. Now, for the past blah number of years, in the very next slide that we have, Nate's going to talk more about this for reasons that will become clear. We've been using timing analysis and resource consumption analysis of different systems to detect things about how the system is running. Namely, we can use timing variances, power consumption variances, things like that, to reverse individual key bits out of RSA implementations and AES implementations. If we could do that to break crypto algorithms, we're in a much better setting when we own the computer and ostensibly the hardware underneath it to detect virtualization. So that first strategy is side channel analysis, to do things to detect places where virtualization perturbs the normal operation of the system. The second strategy is what we call vantage point attacks. And Nate just talked about it a second ago. We have a dilemma here, which is that in order to allow the system to be feasibly implemented, so we don't have to spend 16 man-years actually building it, in order to actually allow the system to be feasible, we don't implement all of the hardware that's supposed to run there. We allow certain requests of the hardware to pass directly through without being intercepted. Well, if you forget important ones, then the actual guest operating system, which is actively trying to detect you, can talk directly to the hardware. And in a variety of cases, the hardware will betray you if you're the malware author. So there are a whole bunch of places that you have to catch and make sure that you emulate, even though to get functionality working properly, you didn't have to emulate them. However, that's the other horn of this dilemma, which is this third strategy we have, which is the fact that as you try to implement those and emulate those different features, there are variances in how those features actually work. So if you don't get those perfectly right, you create differences that we can monitor for as well. So our talk talks about 3 different strategies of places that we're using to detect virtualized malware. Okay, here's one.
We think that all those strategies